Guys, this is chapter 53, part 2, and the focus for this particular section is going to be on demographics, and then how do we tie those demographics into start talking about population growth. So when we talk about demographics or the study of demography, we're talking about vital statistics, particularly your birth and death rates within a population, and how do we see fluctuations within those statistics. So we've got a couple of tools, and a lot of these actually came out of, believe it or not, life insurance companies. So not that any of you guys probably have much experience with that, but you will see that later in life. The idea there was to sort of track what's the population growth in a particular area look like, when do people typically have children, and what's your life expectancy. So that all got calculated into crazy mathematical formulas to sort of say, all right, well, what's the money that life insurance company wants to take from you to sort of ensure that if something does happen to you prematurely, that your family has some money there to help them. But those sort of tools got transferred and sort of reworked to be useful in ecology. So one of the things we can take a look at are life tables, which is what you see here, and this information then got utilized to create this graph here. But these life tables, their whole purpose is to take age-specific summaries within a population. So if you take a look, all right, here's our age in years, and from 0 to 1, here's how many individuals I have actually alive at the start of the year versus the proportion that are alive, the number of deaths that happened, what's the death rate. So at that particular point, your average life expectancy is relatively good. We increase it if you make it between 1 to 2 years, and then as you get older, all right, that decreases again. And what you're really doing with these life tables is summarizing your survivor patterns. And they get constructed by following a cohort. And all we mean by a cohort is it's the group of individuals that are born at the same time, and so we kind of track them. So your grade, whether it's junior, senior, whatever, your group of individuals that are in your class with you, your graduating class, your cohort. And so we could, in theory, track your graduating class for any number of things, and they do. They'll track you guys for graduation rates and number of classes that certain students take, and we use that data for educational purposes. But here they're using it for determining your average life expectancy. Okay. Some of that information can then also get graphed into these survivorship curves. And so we're looking at taking the number of individuals and what's their expected lifespan over time. And what we find is that most organisms are going to fall into one of 3 general patterns. All right, so we take this type 1 curve, and these are sort of your larger mammals, us included, okay, where you've got very few offspring at the beginning, but because we care for them, there's parental care involved, your percentage of likelihood that you're going to die early on in life is relatively low. So you don't see a drop-off in life expectancy until about middle age, okay, or even longer now that, for humans, our medical care and understanding of how the world works has been getting so much better, technology's better, so on and so forth. So you have a relatively high number of survivors early on in life, and then it drops off as we get older. Type 2, there's pretty much an even chance all along that you're either going to survive or you're going to die. So these are sort of your smaller organisms. The squirrel there in the picture, mice, rats, cats, dogs, those sorts of things. So they have not a huge litter, but they'll have a handful of offspring. And some of them will make it, some of them won't. And as we get increasing number of years, fewer and fewer are alive at the time. Type 3 is this. So these are organisms that kind of just spread their seed, have tons of offspring, in hopes that at least some of them will survive to a reproductive age to replenish the population. All right, so they have very high mortality rates early on in life, and very few of them make it much past that reproductive age and also drop off as well. Okay, so that's one way. Now keep in mind that what we're looking at here are really sort of idealized patterns. They're generalizations. All right, but if we kind of stick to remembering that, a lot of organisms are going to fall into one of these three general patterns, or at least somewhere close. Taking a look just kind of a little bit more at these reproductive tables. If you ever come across a table that talks about being a fertility schedule, it's a similar idea. But here now, rather than following all the organisms in a cohort, we're specifically focused on the females. Why? Well, it's going to be up to the number of females in a particular population to really determine what the population growth is going to look like. All right, I can have tons of males, but if there's no females to carry the offspring, or even to provide the eggs to make the offspring, it's really not going to matter. And so they really focus a lot more on the females here, and also looking at how many offspring each female produces. So when they talk about your litter size, that's what they're talking about here. Okay, and you can see that sort of in mid-peak reproductive ages, she's got a lot more offspring per litter, and then it's going to also drop off. Okay, so that's going to have an effect on your average number of offspring per female, and all of this stuff then dictates what your reproductive patterns, what your growth patterns are going to look like in your populations. Okay. So all of these tools then can start help us to explain how populations are growing in a particular area over time. And so we can start differentiating between exponential growth and logistic. Exponential growth, we've got populations that are really in sort of their ideal conditions. So they're not limited by any sort of resource. Predation's not a problem. Disease isn't an issue. They've got all the resources, food, water, shelter, mates that they can ever need. And we study populations that are kind of going through this exponential growth to really start to understand what's the capacity for those species to increase. What are the conditions that are going to facilitate this type of growth? Because when they're absent, we can then start to look at what happens. So most populations won't go through exponential growth, all right, unless they're introduced into a new area or something wipes out a large number of individuals, or there's a huge mass exodus in a particular area, all right. But these are going to produce those kind of characteristic J-shaped curves that you see here, okay. But it's not sustainable. So most populations will go through some period of exponential growth early on, but they're not going to stay there. Okay. So if they're not going to stay there, how can we start to talk about calculating population growth? Well, we can simply look at a very simple equation where we've got your change in population size, and we're taking the number of births plus the number of immigrants coming in, adding those up, and then subtracting that number from the number of deaths plus your immigrants that are leaving, and that's going to give us that dynamic change. All right, or your per capita increase. So if I'm having more births or more immigration than I'm having death or emigration, my population size is going to be a positive number, so I'm increasing. Or if the opposite is true and there's more deaths and or more emigration, it'll be a negative number, and then my population is decreasing. Okay, but we're looking at that rate of increase or decrease, for that matter, over some certain defined period of time. So we can take all of this and look at it mathematically, and we'll do some practice problems with this at a later point in time. But here we're taking your change in population, or that delta n, over your time interval, your change in time, and all we're saying is that change in population size over time is going to be expressed by the number of births minus the number of deaths. And here we're not taking into account who's moving in and who's moving out. We're simply looking at the number of individuals we're adding birth-wise to the number of individuals that are dying off. All right, and so we can sort of express these as average numbers. And that's where you get this per capita growth rate. All right, so your birth rate would be your population size times that annual birth rate. Death rate would equal the per capita death rate times your population size. Okay, and so all of this kind of gets tied back into one another. Spend some time in the textbook. They do a nice job explaining with specific numbers. Kind of throwing this all together now, I'm taking that original equation and plugging in these bits and pieces. So here's my population change over time to include my per capita birth rate and my per capita death rate. Okay, because we're not necessarily going to be capable of going out and counting every birth that happens, every death that happens. Okay. And so all of this ends up giving us this per capita rate of increase. Okay. And if you get what they kind of called this zero population growth, then you're getting the same number per capita of births per your death rate. So your R ends up equaling 0. So there's no population growth at all. When you start to see those numbers shift away from 0, whether they're positive or negative, then we can start looking at how populations are growing. So we can utilize that then to talk about the rate of change in a population size. And that's where this comes in. Now, depending on what our study questions are, we may be looking at an instantaneous per capita rate. Okay, so at this particular moment, at this particular time, all right, we're talking about the change in population given our time interval, and what's that instantaneous rate. The other option then, to take it even further, is to start taking a look at what's happening over time. All right, and so if we're trying to calculate a population and we want to know whether or not we're talking about exponential growth or not, remember that exponential growth is under ideal conditions. We would expect that if we had all the resources, all the mates, all the shelter in the world that we could possibly need, that as a species, as an individual within that population, my reproduction rate's going to be at its max. Okay, so I'm going to max out my possibility to create offspring in order to continue the population. So we're looking at an Rmax, a rate of growth that's at its maximum. Okay, because I'm just going to keep reproducing. So long as I have the needs that I have are met, my resources are met, I'm just going to keep reproducing until I die. Okay, or until the point in time where my body is no longer capable of reproduction. So here is my exponential. I'm at my max. I'm just reproducing and reproducing and reproducing. Okay, and so my population is literally exploding. It's doubling every time we go through a generation. We already discussed that that's not sustainable forever. So what's the more realistic option? That's your logistic growth. So you've got a point of exponential growth. All right, so individuals get introduced, let's say, into a new area. They've got plenty of resources, plenty of food, plenty of shelter, and so they're going to reproduce and double and double and double their population size up to a point where they reach that carrying capacity. Okay, and in this particular instance, that carrying capacity is being suggested that it's 1,500 individuals. Okay, now that's going to vary depending on your amount of resources, okay, depending on the area, depending on the species, so on and so forth. Once we hit that carrying capacity, though, your population is going to kind of stabilize it at that number. Okay, so we're going to grow and grow and grow and grow and grow until I hit that carrying capacity, and then my population is going to level off. Okay, and so that's sort of where that typical S-shaped curve comes from. So when I'm looking at logistic growth, I start with that whole idea mathematically of exponential growth, which is right here. Okay. But now I'm going to take into account my carrying capacity, which is K, as well as that rate of increase for my population size. Okay. So theoretically, I've got a population size, 25 individuals, 1 or 100% being the max rate for reproduction. My carrying capacity and taking all of that into account gives me 0.98. I take that per capita rate of increase, and I can grow with an extra 25. Okay, so that's where that growth rate's coming from. But now, down here, now I've hit carrying capacity. Remember that number from back here. Okay, and so I can't grow anymore. I've reached my limit. That's why that number is 0. All right, and these numbers increase because I'm increasing my original population size until I hit that carrying capacity. So that's where all that's coming from. These numbers are also dependent on the number of individuals in the population capable of reproducing, okay, until I reach that carrying capacity where I can't grow anymore. Problem with all of this is that we talk about exponential and even more so the logistic growth in the sense that these are really idealized, generalized patterns. Okay. They're useful in terms of estimating what the population is going to do over time in terms of growth, also determining what that carrying capacity number should be. All right. Talking even about, all right, I've got to have so many individuals in that population to keep my number stable. Otherwise, I start risking things like extinction, and we'll get into some of that with the conservation ideas in Chapter 56. But the point here is that most populations aren't just going to magically level off when they hit carrying capacity. It's much more dynamic than that. So we're going to have individuals we're going to explode that population size potentially way above, like this one, or just a little, all right, above that carrying capacity. And what's going to happen? All right, population can't be sustained there. We're way above carrying capacity, and so we crash. Well, now I'm below carrying capacity again, so I've got some resources available again, and I'm going to pop up again and down again. And so this particular line is much more jagged, much more up and down than that sort of flattened out line that we see there. All right, so it's a lot more dynamic than that original graph might suggest. But again, it's useful in sort of giving you that visual, giving us that data to work with